Alright, so sometimes when we have objects that are immersed in a liquid, we're interested in knowing how much pressure or force that liquid exerts on the object. And we do it by choosing cross-section, by choosing horizontal cross-sections, because the pressure or the force of the liquid is going to be constant across the whole cross-section. Why? Because there's the same amount of liquid pushing that whole cross-section down, right? So here and here, there's no difference in the pressure. So if we can find the pressure exerted on one cross-section, and we can do it according to this business, then we can just add them all up and find the pressure or the force exerted on the whole thing. Okay? So what is this business? Well, this business says, look, force is just pressure times area. It's just universal. Then the pressure for a liquid exerting some pressure on an object is just going to be dependent on your depth. Okay? So how far below the surface of the liquid are you? That's the only variable. Then there are some constants that we really don't care about. Sometimes they come in different forms. Sometimes they're rho g, sometimes they're delta. For the purpose of this tutorial, I just use c. I just said I don't care what kind of constants because you're not going to do anything with them. You're just going to pull them out the integral, just leave them until the end. You just don't have to forget them. You have one job, not to forget your constants. But as far as we're concerned, I'm going to call them c. So those constants times the depth. That's the only thing that your pressure is dependent on. So your force is going to be the depth times, or your constant times the depth times the area. Okay? So for each cross-section, it's going to be the constant times the depth times the area of the cross-section. Right? The cross-section is, if you think of it as a rectangle, it's going to have some height, the dy, and some depth or width, or I'm sorry, width rather, which is your width. So the only two things that we have to figure out are your depth and your width, and then the bounds. But the bounds are very easy. Okay? So let's go ahead and do this example. We have a little triangle shape immersed in the water. We're going from y equals 0 to 30, because that's just what the height of the triangle is. Now, if this triangle had some sort of offset like that thing does, then we would have to do some additional work. We'd have to pick our 0, whether our y equals 0 is going to be at the top of the shape or at the top of the surface of the liquid. But here we don't have to worry about that. We'll worry about that in the next example. Here we'll go from 0 to 30. Our depth, what is our depth? Our depth is just going to be y, because that's how far below the surface of the water we are. What about our width? Now here is where you're going to do most of your work, the width. We need to derive an expression that's relating width to the depth. Okay? We can do that. We say, okay, I need something in terms of, or I'm going to actually call it y, not d. It's relating y to my width. Well, when my y is 0, this is what I do know. When my y is 0, my width is also 0, right? Right there. And when my y is 30, my width is 10. And this thing is changing linearly. Our relationship is linear, so we can just draw a line, right? Going back to algebra 1, we can just find a line that intersects these 2 points, and we got ourselves the relationship. So how did we do that? We needed the slope and the y-intercept. What's the slope? It's delta y over delta x, or delta w over delta y, because it's just you're dependent over independent. So dependent is w, so w is going to equal delta w over delta y. So 10 over 30 times your y. It used to be mx, but now here's my, because that's my independent variable. And then plus the y-intercept, but that's just 0. Okay? So it's just 1/3 y. So that's going to be my width. And that's a pretty easy integral to do. Okay? So let's go ahead and do this more sort of complicated example. It's just different. It's not complicated. So we have a circle immersed in water, 1 unit below the surface of the water, and its radius is 2. So what we're going to do is, this is something you just have to sort of know. When you have a circle, you should pick the center of your circle as your y equals 0. The reason is because then you can use the symmetry of the circle. Okay? You don't have to go from, if you choose here, the top of your circle to be y equals 0, then you're going to be going from 0 to 4, and you can't use the symmetry of the circle. But now here you can go from -2 to 2, and use the fact that, actually you'll see in a second, I'm not going to ruin it. So I'm going to go from -2 to 2, and I'm going to have some constant, this is force, some constant times my depth, my width, dy. Okay, what's my depth? Well, the depth is just going to be y, but remember, here we have an offset. So it's going to be y plus our offset. What is our offset? Well, there's the 1 unit offset that the shape had, but that's not all. We also gave it a 2 unit offset when we chose our 0 to be here. So in total, we gave it a 3 unit offset. My y equals 0 is 3 units below the actual surface of the water. So my depth is going to be y plus 3. Again, 3 is my total offset. What is my width? Well, here again we have to do some work to get it. We don't have any points or lines here, but what we do have is a relationship that has to be true. Namely, it's x squared plus y squared is equal to 4, right? Because the radius is 2, 2 squared is 4. So my y squared plus, now I don't want to use x squared because that doesn't help me. I'm going to use width. But x doesn't exactly equal width. Okay? So if you think about it, whatever your x coordinate is, if this is 0, whatever your x coordinate is, your width is twice that. Okay? So if I have this guy, y squared plus x squared equals 4, and I also know that my width is twice my x, then I can just say, it's just w over 2, right? Think about that one. This jump is a little subtle, so make sure you, if you don't understand, go back and make sure you understand it. So now I just got to solve for w. So w is going to be 2 times square root of 4 minus y squared. Done. Got my w. And now all I got to do is separate these little integrals, or actually make 2 integrals out of this one big integral, and then solve it. So it's going to be c times the integral going from -2 to 2 of 2y 4 minus y squared dy, plus the integral going from -2 to 2 times 6, of 6 times 4 minus y squared dy. So I'm going to notice something really quickly over here, that this guy is just, actually I'm going to take the 6 out, that this guy is just the area of the semicircle, the right semicircle, because it's not the full circle, because it's just plus square root of 4 minus y squared, not plus or minus. Okay? So the area of this is just going to be 4 pi divided by 2, 2 pi times 6, 12 pi. And over here, I can just do an easy u sub and say 4 minus y squared is my u. My du is going to be minus 2y dui. And I can solve that pretty easily. But what I will find is that because of the presence of the y squared in the antiderivative, and me going from -2 to 2, which are the same number when I put them in the y squared, I'll get 0. Right? So this is just going to be 0. So my answer is just going to be 12 pi. So as you can see, there is some work involved, but the main points that you should take away from this are choose your center carefully, or choose your y equals 0 carefully. If it's a circle, make sure you're taking advantage of the symmetry of the circle. Here, you don't have to worry about it, but this could be offset a little. Now you have a choice of whether your 0 should be the surface of the water or the top of the shape. Okay? So do that carefully, and besides that, the width is basically your only piece of work that you have to calculate, and you're just trying to find the relationship that puts width in terms of the depth.